Okay, hi Professor Wellman, this is Erin O'Neill, and I'm going to talk through Lab 5, questions 4 and 9. So in question 4, we were to make a chart that graphed the values for the kinetic energy, gravitational potential energy, and electrical potential energy of these two particles, these charged particles, and how they related to each other over a change, like a changing y, so increased distance. So this is the graph I came up with. As you can see, the constant energy throughout remains the same because it's constant. And then the gravitational potential energy is linearly changing since it's linearly increasing distance by 1 millimeter at a time. And then you have inversely related curved lines for the electric potential and electric potential and kinetic energy. So if you want to see a little more deets, this is how I did it. Just basically plugging in the numbers here. I can talk you through it all. So to find electric potential energy, it's K times charge 1 times charge 2 divided by R, or in this case, we'll call it Y. So there's that. And then gravitational potential energy is mass times gravity times the change in Y. So there's that. And then kinetic energy is half of the mass times the velocity squared, which this one was just 0. Oh, gosh, I hate it when it does that. See if I can get it to give me the deets. Here we go. Oh, but you know what I did here? I just found the constant energy and then subtracted electric potential and gravitational potential from it because I knew that the resultant would be the kinetic energy since it's all conserved. So, and then, yeah, I think that's all I have to talk about right now. And then this number, yeah, I just plugged in because I think I found it. When did I find it? Anyways, I found it at some point and then I plugged it in throughout. Okay, so that was that one. And then number 9. So even if you start off with the two particles, the charged particles being closer together, it's interesting that like you'll start off with a higher potential energy, but because energy is conserved and your gravitational potential energy is lower, ultimately, it will shake out to be the same and shake out to be the same speed and like motion as it moves through space, because I'll go back. You can't see all my graphs here. Here's one too. Here are the two graphs I use just to like show comparison between them, but I'll actually show you here because it's a little easier to see it all. Well, will it be easier? Maybe not. I'm gonna make this smaller. Okay. All right, thanks for hanging in with me. Here we go. So, for example, when y equals 0.02 meters, Even if we started at 0.015 meters, and here we started at 0.005 meters, if you continue the, change in energy carrying through the F-net and finding the acceleration is the same once it catches up to this point. Oh, there we go again. But so 0.20 meters, you have 0.005 newtons, whereas here it's the same 0.005. Yeah, this one was a bit of brain twister. I started out doing it in the Google Excel folder, and it really did not work well. So went through it all a second time and learned it that much better. Okay, thank you.